live. Yeah, we're back. We're live. It must be Monday. Oh, and it's Labor Day. We decided we'd schedule broadcasts today, and we found that the School of Ocean, Earth Science, and Technology at UH was willing to do that too with us.
We never rest.
I guess so. You know, out there in the world of space, they don't know from Labor Day.
Oh, no. Weekends, Labor Days, doesn't matter. In fact, when my wife drops me off sometimes, like on a Sunday, the parking lot behind our building is full. And all she does is mutter, nerds.
Yeah, but this is a good sign. It's a wonderful sign of a great quality school.
People love what they do.
Yeah, totally committed.
Yeah.
And they're compulsive about it, which compulsivity is a really good thing.
Yeah.
I'm happy to hear that. You know, I remember it being said that on a given Friday afternoon at the Manoa Innovation Center, the parking lot was empty, and I was very concerned about that. You want people to be there working hard.
People, and thinking about it all the time.
Yeah.
Yeah.
Yeah. 7 days a week.
In fact, one of my colleagues and I have a term for it, for waking up. We wake up in the middle of the night and thinking about what you're working on.
Oh, yeah.
So we call it thinksomnia.
I love it.
And it's a good, and so we embrace it. You just don't try to fight it. Get up, get this bee out of your bonnet, and go back to bed. Because it's the, you know, when your mind is always working like this, it's a, and I know lots of scientists who do this. I'm sure people in other fields too. When you're thinking about things, you start incorporating them into your dreams.
With me, I do this all the time, you know, 3 o'clock, 4 o'clock in the morning. No reason other than there's a bee in my bonnet, and I have to get it out. I have to get to a laptop and type out my thoughts, or I'm afraid to lose them.
Oh,
that's what
you
keeps
got it
me
right
up.
there. I have a little pad next to my side of the bed, and I flip it open and write the thought. It's messy handwriting because it's dark.
Well, you got to be able to read it in the morning, actually.
So I try to write it neatly. Other times I just get up and have to actually do something.
So let me ask you a question. That's Jeff Taylor, if you didn't get it already. He's a professor of planetology at SOWEST. That's the School of Ocean, Earth Science, and Technology at UH Manoa. And we call the show Research at UH Manoa. And today we're calling it Planetology Needs Public Relations Too. But when you get up in the middle of the night with the bee in your bonnet about science, and you start writing on the pad, what kinds of things do you write?
Oh, that's an interesting question. I should have saved. I should have archived all these little notes. Some of it is a diagram. One diagram. Here's a cool thing I actually thought up middle of the night was a diagram of. Are you ready for this? This shows maybe I don't sleep so soundly. A plot of for lunar samples of thallium against cerium, and you're going to say, God, what's your problem? But these are two interesting elements that behave the same geochemically, but actually one's very volatile. And when the moon was made, it lost these volatiles. And so I made this plot of thallium against cerium, compared it to what we have for Earth lava flows, basalts in particular, and they are drastically different.
So what was the aha that you had to write down? What was the special moment?
Plot. I was having trouble showing in some kind of really coherent way the variation of the difference in thallium in the moon and the Earth, and to get rid of all the things that happen after you make the moon. You know, everything gets rearranged. Well, these two elements follow each other, and so, and they represent the before the moon and before the Earth formed. They were always coherent, these two guys, until one separated because it boiled off. So anyway, the aha was really to make that plot one against the other. And
that advances
it worked
your
out.
study.
It's great. Yeah, because the moon one, if thallium's there and the cerium there, the moon one lies flat across the axis, and the Earth one is spunk like this. The slope is a factor of 100 different. I mean, this shows that this element that we don't often think of was lost when the moon formed. And so it tells us something about the origin.
You know, I like to make a footnote question on all of that. It only dawned on me, and I'm not sure about it either, recently, that when we have the periodic table of elements, that applies across the board in our solar system.
Yeah.
So you could find elements that we have on Earth in other planets, and vice versa. And every element, am I right about this? Every element on every planet is on the periodic table.
Yes.
Isn't that amazing?
And even more amazing is not only are the elements the same, but their relative amounts differ from planet to planet.
Sure.
But the minerals they make are the same. Except for the Earth has a whole bunch of them that are made because it's so wet, so much oxygen, and a lot of biology that really affects the mineralogy. But if you ignore that part, the planets don't differ in the minerals present even.
And then it opens the question of whether other solar systems, what do you call it,
Extrasolar planets. Yeah.
Exoplanets.
Exoplanets, yeah.
In other solar systems and all that, whether they have the same elements or whether they have different elements that jump like a beam, that do different things, that have characteristics that are not the same at all, and that when introduced into our solar system would have unpredictable results. What do you think? Does anybody know?
We know other stars, and except for some short-lived isotopes that we do know about, like californium, all these things, beryllium, all these transuranics that are made in reactors and accelerators and decay fast, those are present in other stars because they're some are young, some they just made them, and so you see some of that. But except for that, the elements seem to all be there, but they do vary in their amounts. Young stars from fresh stuff have very little of the heavy elements like iron, but they have more carbon. And so there's a big debate about how much of the astronomers are like this. Most of us call a metal things like aluminum chair, an iron bar, right? And not them. Anything heavier than helium.
There's a lot of
That's
things
a
that are
metal.
heavier.
They call it metallicity, and how much of that. And what they mean is that hydrogen and helium combine. The hydrogen combines to make helium by fusion, and helium combines to make these heavier things. And the more of that you make, you have to make iron, you have to really kind of recycle a star a couple of times to build up the amount. And you don't make planets if you don't have enough of the metals, because there's not enough to make these rocky objects.
Yeah, right.
If you have nothing but hydrogen surrounding a star, it'll just either go to the star or dissipate. Whereas if you have these other things and they make solids, then the solids start coming together, making planets.
So for me, it's only deduction, but if the periodic table is in our solar system, and it's sort of, it includes the periodic table, but it's limited to the periodic table. And then we find that in exosystems, we have the same elements, or it looks like we might have the same elements. If I one step of my logic is if we find it all here in this system, then we could make some kind of cockamamie conclusion that it all came from the same mass, the same body of elements, and it all flung out into space. I don't know if that's true, but then the question is, if we find that other systems, exosystems, have the same elements too, we could say, well, they were also part of this original mass that flung out to space. Is there anything to any of that?
There is that everything is part of the same mass that was flung after the Big Bang. And we know that because everything's going away from each other. And you don't really need to know about the elements. But the elements, they're made over time, except for some burst of element formation because of but after the Big Bang, it took a while to make the atomic particles. It's not so straightforward as you make all the elements at once, and then we just keep mixing and matching them. They keep getting made as stars evolve.
By a process of what? By explosions?
By supernova explosions. They send their debris into interstellar space, and then eventually another star and a solar system will form. Actually, it's usually many stars and solar systems form from that. And then they end up, depending on the size of the star, living a shorter or longer lifetime, having planets or not planets, and then they do the same thing. And there's red giants, stages and all that.
It strikes me that you're a really good teacher, actually, Jeff. You must be teaching this stuff at SOWEST.
Yes, and we have people who work. This reminded me when I used the word isotopes, which, by the way, are wildly complicated things. But I have colleagues who spend their time analyzing the isotopes that no longer exist. Now,
Whoa,
that does sound like a
that's
nerd
really
pursuit, doesn't it?
Oh, wow.
But they have, like for example, the most famous of them is aluminum-26, isotope of aluminum. The common one we have that make long furniture is 27.
Can you define an isotope for the people,
yeah,
including me, that don't know exactly what it is?
Isotopes are atoms whose nucleus, where the protons and neutrons go, the isotope has a mass dependent on the number of protons and neutrons. And then surrounding that, to make up the atom, they have electrons that balance the proton charge. And so aluminum-26 has one fewer neutrons than aluminum-27 does.
If that makes it unstable?
And it's unstable, yes, and it has a half-life of 700,000 years. Now, in the early solar system, we have definitive evidence it existed because it decays to magnesium-26, and there is, in certain rocks, in aluminum-rich minerals, you find an anomalous amount of, this excess magnesium-26. Well, where does it come from? And it's correlated with the amount of aluminum. So it comes from the decay of aluminum-26. Is this wild?
It is wild.
And because the half-life is so fast, they can detect differences in the timing of events in a very early solar system that differ by 100,000 years.
So if you look at it over a long period of time, the universe is all dynamic. It's all changing all the time.
It's all, yeah, things are always changing. That's the thing about geology. I mean, we sit on an island here that used to be located where Kilauea is now. I mean, we make an island, it moves to the northwest on the Pacific Plate, and that's very dynamic. I lived in Albuquerque, New Mexico, and there was a limestone deposit on top of a 10,000-foot mountain east of town. That limestone, and it was deposited in a shallow sea 60 million years ago. Well, now really, that's a pretty amazing thing. And the other part of that limestone is located 3 miles beneath the valley floor. So this, not only did you have a sea there, and now it's all uplifted, but you uplifted a whole block of it, 4 miles or so of difference in a gigantic block of rock, lifted up. Now it didn't happen in a catastrophic event, but it's a big event, when you think of it.
Yeah.
It's a dynamic place.
If you're going to be a geoscientist, you have to have a different view of time.
Oh, you do. Geologists are and planetary scientists, astronomers, they're the only ones who will put the word only before something like a million years.
You heard it here on ThinkTech. We'll take a short break. That's Jeff Taylor, professor of planetary science at SOWEST. We're talking about planetary science needs public relations too, here on Research in Manoa. We'll be right back. We're going to find more out about him and his friends and the work they do and how they do it and what we should be thinking about it. That's a mouthful. We'll be right back.
Aloha. My name is Josh Green. I'm a senator from the Big Island in the ER position. Every other Tuesday, I get to host a show here on the ThinkTech program about healthcare. We call it Healthcare in Hawaii. It's really enjoyable for me to bring other healthcare leaders from around the state to talk about our pressing issues. Hawaii has long been the health state, but we need to keep up the momentum, the inertia, and with your help and with your participation, we can come and share all of the big issues that are pressing day to day. Thanks for joining us every Tuesday, alternating weeks from 2 to 2:45.
Hi, my name is Stan Osserman, and I host the show every Friday here on ThinkTech Hawaii called Stan the Energy Man. We talk about everything energy, from anaerobic digesters to batteries to hydrogen fuel cell and grid power. And we do that to keep you informed on the latest technology that's out there and the things that are going on in Hawaii. We broadcast every Friday from noon until 1 o'clock, and I hope you'll tune in. So sometimes we'll be on ThinkTech, and sometimes we'll be on Olelo Channel 54, and I'd like you to listen in to me and join me every Friday. We'll see you then. Aloha.
I told you we'd be back, and yes, we're back. Like MacArthur, we came back. And Jeff Taylor is going to tell us about planetology. But one of the things that I think comes out of this is that everything changes, I guess what I want to say is everything needs water. I mean, I suppose you would find water on most planets in one form or another.
Oh, well, yes, but it's not very much in some places. Like the moon has very little, although there's something of a debate about how much is on the moon, but it is there. We used to think there was none. I mean, really, virtually, literally none. But now it is clear because naive people who didn't know better measured it with modern instruments and said, well, there is water on the moon. And
well, I mean, not to say that it really supports life, but one thing
you do need a lot.
You need a lot
to support life.
And we're built to live on Earth, which has a certain maturity, I guess, in this. But it strikes me that if all the elements are, you see when I'm dwelling on this issue, if all the elements are the same, and we found that over time, long periods of time, elements may change from one to another, then you can take modern science and actually make them change faster. Not in a million years, but in maybe seconds or minutes. Then you could change the nature of these planets with that kind of science. I mean, this is very futuristic, but don't you think?
You could, but you don't make so much new elements as you redistribute the ones that are there, I think.
Atomically?
Yeah, chemically.
Chemically?
Yeah,
Okay.
yeah. Well, for example, there's an excellent experiment we're doing on Earth. We're increasing the carbon dioxide content of the atmosphere.
And why would you want to do that? Oh, you mean everybody's doing it, like it or not?
We are, like it or not, we're doing it.
Yeah.
And on Mars, you could do the reverse and actually add oxygen to it. And so if you started, one of the big events in Earth history was a giant oxidation event that took place when some single-cell organisms, what became blue-green algae, decided to well, look, I could use sunlight and to get my energy rather than chemical reactions with rocks and each other. And so they this made a big difference because the byproduct of that was oxygen, and that changed the course of the history of the surface of the Earth, and led to a really much more diverse and robust life on Earth.
I don't know, how promising this technology is, science is, but I heard on NPR last week about a guy on the mainland, scientist, was making a process which would take carbon dioxide and water, I think it was, and maybe a third substance too, and out of that he would be able to create oxygen.
Oh, you can there's even mechanisms on Mars to do a number of, and it's been tested, not on Mars, but tested. It's easy to simulate Mars, where you react hydrogen in any form, could be methane, could be something, with carbon dioxide, you make oxygen.
That's it.
And
That's
so you can do that. You can do the same thing. You can reduce water if you find it anywhere and split it into hydrogen and oxygen for life support. And the two of them combine again to make a rocket propellant, which is the common, powerful rocket propellant that many rockets use.
It sounds like this is something that's going to get more popular
that
as we go
probably
forward.
could be done. It's the only way to have a long-term population on another body is we have a great infrastructure here, which is why we're here, right? With oxygen can breathe, a lot of water. Well, you have to kind of get those things going on Mars. Mars has a lot of water, probably as much as the Earth.
Is it pure? Is it good? Is it drinkable?
No, some is, no doubt, because some is deposited from the atmosphere as ice, and others might be mixed with other stuff, so you'd have to clean it up some.
Yeah.
Others is combined in minerals, because a lot of minerals, like all the clay minerals that make up a nice, beautiful red soil we have here in Hawaii, they have water-bearing minerals, and so you could get water out of those too. The moon's a little trickier because it doesn't have as much.
Let's do a picture show. I have the sense that we have some pictures here. We've been looking at some of them casually, but this may help to describe your work these days.
Well, I like that one. This is, see this group of people? This is in 2 weeks ago in Woods Hole, Massachusetts, where we had a science team meeting of a mission called GRAIL. The woman in front in the orange, see her?
Mm-hmm.
That's Maria Zuber. She's a professor at MIT, now also vice president for research at MIT. She's the principal investigator of a mission that was sent 2 spacecraft to the moon. It's called GRAIL, which is an acronym for gravity and other words. What does it? I never remember it, but
It's relative gravity or?
it's absolute gravity.
Absolute gravity.
Gravity is a big deal because you can measure, it allows you to see beneath the surface because there are excess. This is the GRAIL's logo, and I have that in here because,
Look at
well, there
that.
it is, Gravity Recovery and Interior Laboratory. See the 2 little things above the moon? That's the moon there.
Yeah.
Those are 2 spacecraft. They're about the size of washing machines. They followed each other in lunar orbit for about 6 months. And then their orbits had to be trimmed a lot to keep them in orbit because the gravity field is very irregular. There's a lot of concentrations of gravity around the moon, and so things go up and down and get out of, they can crash into the moon in a month. So you have to keep doing that. And they ran out of gas, and so they crashed them into the moon. But they measured by radio signals to each other. They follow each other by 60 to 120 kilometers. And they could measure their relative velocity to a micrometer per second. It's
That will determine gravity.
and you determine gravity because one spacecraft is being slowed because it's it's decreasing its orbit because of the mass pull of the gravity, and the other one might be not changing, but it changes relative to each other. And they can see this slight difference in accelerations and velocities with amazing accuracy. This was modeled after a mission that was done for the Earth called GRACE. The G is gravity. And it measured the field of the Earth really good, but not to the same spatial resolution as the moon one, because the moon one could fly lower. The Earth one, you have to be above the atmosphere, otherwise the satellites decay. So it's there, and the last orbits, right before the crash, last few were 2 kilometers, right? So that's like a mile and a quarter or something above the surface, about the highest point along its track, just to get a close look. And then finally it crashed into the moon. You have to get permission, by the way. This is a funny story. And it does show your government at work and how efficient government always is. So Maria Zuber,
Make notes.
Maria Zuber and her team asked permission. You have to have an end of mission plan. NASA insists on it because they do not want spacecraft crashing into heritage sites like the Apollo landing sites. That's a good thing. It's a very good policy. And so they had the plan. They say, here's what we're going to do. We know, and here's why we know it's going to crash way far away from those places. And it did. And finally, 1 year after they crash landed, the 2 washing machines, they received the official signed permission from NASA.
To land. And all is right in the universe. How'd you get involved in this stuff, Jeff?
I was a physics major in college, and I took a course in geophysics. And I said, well, this is it. This is great. And the guy geared it towards, how do you know what the Earth is made of? Inside. And I thought, this is just the greatest problem I've ever heard. And so I went in, and that just kind of led me into meteorites, and then we got the moon samples, and now we have Martian meteorites too. and numerous spacecraft that measure chemical composition from orbit.
So as a geologist, tell me the story by which you took your degree and came to Hawaii, came to UH Manoa.
Oh, that's a longer route. I went to graduate school in Houston at Rice University and worked on meteorites there, but it was good fundamental geology, geophysics education at Rice. And then I did a postdoc working on moon rocks at what's now called the Center for Astrophysics, Harvard-Smithsonian Center for Astrophysics in Cambridge, Mass. And then I did a stint at Washington University in St. Louis.
That's a good school.
It is a great school. It is assistant professor, and then moved to New Mexico for 14 years. And in between, before I came here. And there it was a research job associated with the Department of Geology in an outfit called the Institute of Meteoritics. And we worked on moon rocks, meteorites, and it was a great job.
It's a great location.
It's a great location, and New Mexico likes to brag about being multicultural. You know, the three races: the Native Americans, the Anglos, Latinos. They don't know diversity, do they?
No. Nobody knows it like we do.
And so then I moved here 25 years ago.
Oh, that's a
Whereas the university, they gave me an award, 25 years of mediocrity. I thought that was a little insulting. There was no reason to write that. No, actually.
But you've seen it. Go ahead.
Actually, UH does give, you get a 20-year, you get a co-op pen. But you don't get anything at 25. And it turns out, the pen's out of ink. They could at least give a refill.
Well,
So
at least a refill, a 5-year refill. Fair is fair. But you've seen it, in 30 years, you've seen SOWEST, bubble up to a national name.
Oh, yeah. It had, I came right as SOWEST had just been organized. But before that, it had a great reputation as the old Hawaii Institute of Geophysics. And of course, our part of SOST that I'm in is the Hawaii Institute of Geophysics and Planetology, a research unit that was established by the state legislature, along with, I think it's the Hawaii Natural Energy Institute, maybe. So it's kind of.
Yeah, okay. I didn't realize that. Yeah.
And so the research institutes that do a lot of training through graduate education, and we do some undergraduate teaching too, most of us through the Geology Geophysics department. But anyway, SOST then took that over. I don't know the whole history of exactly why the school was formed, but this is a powerful, great organization with it's very broad reach. We go from the stars almost, and we go through the history of the Earth before the solar system formed by our guys who study all those extinct isotopes. And we have cosmic dust samples, they're called, and some of them are interstellar dust grains in meteorites. Isn't it wild?
That's exciting.
And so we go from there through the interior of the Earth. We have, in our HIGP outfit, we have a great high-pressure physics group that studies what happens to Earth materials when you squeeze them.
Talked to them.
Oh,
yeah,
like
yeah,
Jim McDura.
Yeah.
And these guys are great. And then we understand the surface of the Earth, the volcanology. We have very good volcanology in SOST. The oceanography people really do understand all the physics of the waves, the chemistry of the ocean floor, which is, of course, a geologic problem as well. So it's so many things that tie together. And I think this is the value of UH, is that I think it's people who stay here in Hawaii actually are friendly. I mean, if they're too uptight, they can't handle some of our unique ways of doing things, but this leads to people who are friendly, and you can make collaborations really well.
Right.
I mean, we have
It's all
strong
about
collaborations
collaboration.
with astronomy. I'm on a student's thesis committee who study exoplanets, and And plus Karen Meach, who ran our astrobiology program and is a very imaginative scientist. We do work with her. There's star formation people work with our meteorite people. And I think that and within SOS, though, those collaborations are very strong and very widespread.
Well, we're lucky. I mean, we have a state and an environment here in the Pacific, although it's isolated. Maybe the best thing is the isolation, where we have a diverse environment with all these diverse, things to study. And the forefathers of SOWEST knew that there were great possibilities there.
Yeah.
And here now we have SOWEST who's in touch with everybody in every place, and in the last 30 years have seen collaboration rise to new levels among science, all kinds of sciences.
Yeah, and it's the future. You really can't do your own little thing.
Yeah.
No, that's actually what attracted me to planetary science. You got to know a lot about different things.
Yeah.
And you can work with other people, so you don't have to become an expert in every single thing. But there's so many processes that interact. Some are physics, some are chemistry, some are biology, possibly including
I still want to know your methodology and your tools. So instruments, whatnot. Your favorite ones. I know there's lots of them. So we're going to take this short break here at half past. We're talking to Jeff Taylor, professor of planetology science, planetary science. Planetary science. You can take his course. I think you should do that. At Manoa Research in Manoa, talking about planetology today. We'll be right back after this break, and we'll find out exactly what he does in the laboratory of his science.
Hi, I'm Ethan Allen. I host Likeable Science on ThinkTech Hawaii, and I do this because I care about science literacy in Hawaii. I want to spread the understanding that science is an interesting part of everyone's life. I want to make sure the broadest possible spectrum of people understand the beauty and the value of science and realize that science plays out each and every day of their lives. I want you to understand that science is fun. So we bring onto this show each week guests who are scientists, from astronomers to zoologists, and we talk about what they do and how they do it. But most importantly, we talk about why you should care about their work, why you should see that their work has value and impact on your life. So I hope you'll join us Fridays, 1 p.m. here on ThinkTech Hawaii. You can watch us via live stream. You can watch us recorded on Olelo, and you can see us each week. We hope you'll join us.
Okay, we're back and we're live, and we had a great time during the break, and I'm sorry you could not have joined us then. But Jeff was telling me about, the whole notion of building software. And in fact, in his family, in which there are 4 kids running around all day, they got to keep track of each other, so they built an app to do that. His daughter specifically, and they went out and they actually spent money to do it. They got programmers, and they built it, and now they know where each other is.
Yeah, yeah. It's called. If we can see the last number 12 picture, there it is. See that? Who has the kids? They have. My daughter has 4 kids, and they had 3, and wanted to have they had 2, wanted to have a third, and they did. Just that the guy came with a brother. So
surprise.
So they're in soccer. Their daughter has a horse, and they have after-school activities. And they would give Bean. She and her husband being driven crazy. And then there's the carpool people. There's the after-school care. All the, how many of these things that you have now. So they kept saying we need an app, and so they designed it, worked with programmers, and have it online. So if you want to go find it,
What's the name of the app?
Who has the kids? When I Googled it a couple of days ago, it came up 3rd on Google. And so you go, it's available at the App Store, iPhone, the Apple one, plus also the Google Play.
And all of this, really to indicate that these days, you can't do much without technology, without software. And scientist after scientist comes in, they sit in this chair, and we always come to the same conclusion, that it's the software that really counts. But tell me about your software. Tell me about your special software sauce and your special equipment that you use to do your research as investigator in these issues.
Well, it's an interesting thing that planetary sciences uses tools that range from things you send to the planet to things that you get back from the study the rocks from the other planets, whether collected by astronauts or collected by robots, or come to us for free in the form of meteorites. Quite the bargain, just that you don't know where they come from.
Do we like free?
Free is good, but not for faculty salaries.
Is this your
Faculty
website
salaries. Oh, this is our, also to advertise planetary science. We have been funded since 1996 to put out this site, Planetary Science Research Discoveries. I do this with my colleague Linda Martell, who does all, speaking of programming, she does all the webmastering of this and keeps it up to date too. You know, because there's styles
You
and
always gotta be changing
you got to
it,
keep
yeah.
and so we have well over 200 articles. And what we do is to take a published article that is in a science journal, translate it to English from the original geek, and
What a great idea.
and then we
make it public.
and then it make it nice and clear, but we tend not to. We don't water it down so that it makes it oversimplified too much.
Yeah,
You know, you have to
yeah.
do some.
Yeah.
And then we define terms, like we were talking about proton before. We have, I don't know how many terms. We must have several hundred in our glossary now.
It helps you though.
And it really is great. And we keep pushing it. And so if you want to learn about planetary science, go to www.psrd.hawaii.edu, and it's all there. And it's in and we get a lot of planetary scientists reading it themselves because we've summarized the articles for them, and especially like people who look at the surface morphologies of planets and impact craters and volcanology. They don't know a lot of this meteorite, like these pre-solar grains and stuff. So they read those, and it's a nice, digestible way to read it. And students studying for comprehensive exams use it, even though we aim this for the public. And we do get 60,000 hits a month.
Oh, a month.
Yeah. So it's
Let me
it's
do
not
the
bad.
math on that. That's a lot per hour.
Yeah, it actually is pretty good. And we get this 5,000, we make PDFs of the articles as well. We get like 5,000 or I think downloads per month. And those are completely unique. You know, no one says, oh, I need another PDF of this. You know, it really is a unique thing.
I was going to say that, you know, in your science, in any science, people don't know what scientists do. I mean, you figure in sort of broad base, you know, you teach, and not all scientists do that, but you can teach, and then you can research. Okay, but the other leg that comes to mind, at least for me, is you got to read. You got to read, you know, email, you got to read articles, you got to keep up with everything that's happening in the world or you're behind.
And you have to be able to explain things clearly. And I think we should share it. I mean, because that's why we did this site. We were actually motivated not just to get funding, although that is a specialty in SOST. You know, we do
With
get
good cause.
Oh, just as long as they mention money, SOST brings in $5 of outside funding for every dollar the state spends on us.
Interesting.
It's a tremendous impact to the
Yeah.
state's.
Why is that? I mean, what makes that the leverage so great?
It's a lot of this money we have a permanent staffs that are funded both through UH and through RCUH. That is hundreds of people, and they're funding work on research projects and through federal grants. And we have postdoctoral fellows, the graduate students, and they're.
It's this research that
research.
is the subject of the grant applications, and the
Yeah.
grant applications is what gives you. So in order to get that kind of leverage, you have to be doing a substantial amount of research.
Good
in the first
research
place.
that gets reviewed well.
Yeah.
Because, it goes through this complicated peer review,
Yeah.
very critical peer
Yeah.
review process.
Yeah. But if in order to get reviewed well, it's got to be written well, don't you think?
Yes.
So that means that the guys who are doing this research not only have to do the research, but they have to explain
You
it.
have to be able to explain it, yeah. But anyway, we try to do this with our website to get the word out to the public about what great things go on in planetary science. Around the world, we have a little bias towards U.S. investigators because NASA is funding us, and, we want to promote that. But, it's inevitable, though, that something great happens. Other countries do great science. And so we do bring that up, too. But it's very fun to write these, and people do like this site and compliment us on it, except for one high school freshman who wrote us. She
I
said,
can't wait to hear this.
It was I can't remember her name. I wouldn't say it anyway. She wrote us, it could be 10 years ago now. She said, all I wanted was some information about Mercury, but all you did was blab on and on. Blab, blab, blab. So you can't please everyone.
Should be a PhD one day soon.
Yeah.
So you know, on that notion, why should she be excited? Why should she like what you're doing? Why should she care?
It's the history of other worlds, you know. It's kind of the big world around us. You know, you learn something, especially true in Hawaii. If you grow up here, and you never leave it, you have one perspective on the world. You make one trip to L.A. or Vegas. That's more likely.
I was going to say New York and Brooklyn, but whatever.
Well, that's the apex of civilization. I grew up on Long Island. So anyway, actually anywhere else, or including Japan, anywhere else, it just opens your eyes to the world. Well, in a sense, your natural world is the same thing. You think you know the Earth, you think, it always has water, we always have biology on a planet. Well, you go to the moon and it really is pretty dry, even if it does have a smidgen of water. And it really is, it's just so different. Everything is much older. There's no young rocks. And it's been bombarded, it's covered with a fine-grained powder all over the place. Mars is completely different from Moon or the Earth. I mean, it has volcanoes, we recognize them. But even that is cool. The mere fact that it's kind of like you were talking about with elements. The mere fact that we have volcanoes that operate the same on Mercury, Venus, Earth, Moon, Mars, and even an asteroid, though we don't have the record of that because
they come and go.
Isn't this wild? But you have the process operates. You know, it's kind of it's almost reassuring. Maybe there's some differences, though, because the planets differ a little bit in composition, and that's interesting, too. But just the mere fact that you have impact craters everywhere, wind blows everywhere, at least we have an atmosphere, and in fact, you don't have an atmosphere everywhere. That's interesting, too. You know, it just opens your eyes.
It's a frontier.
It's
people always want to go to the frontier. They want to see the next step. It's like going west. Sort of manifest destiny. Try to see things you've never seen before. There was a line in Star Trek along those lines. Go places where we've never gone, see things we've never seen. I think that drives humanity.
That's what drives us,
yeah.
It drives us even to make discoveries of, a lot of discoveries in medicine were made because somebody was curious, that led to discoveries in medicine, were made because someone was curious about how cells worked. Yeah. And not because, I'm going to solve.
So I guess to me that's really important. It's not so much that any given experiment, sort of like the one on gravity, is going to result in a better television set. Nothing like that. It's that it's going to give us a more expansive view of the universe. We'll understand things about the world we live in. We'll be able to see things differently, and then we'll build a better television set, ultimately, because of what we found out.
Yeah, it's just that's what makes us human, we're curious.
Yeah, that's Jeff Taylor. He's definitely curious.
You're not the first to say that.
Professor of Planetary Science at SOWest, here doing research in Manoa. So nice to have you on the show. Thank you so much, Jeff.
Thank you, Jay.
Aloha.